Hello everyone, welcome to my YouTube channel. So we are continuing on the deep learning with Pytorch series, and this is episode number 12. So in this episode, which we will be going through is the neural network optimizations, process variations, like what are the different types of process variations are which you can do while training a neural network, and what are the different types of optimizers that are currently available, which are generally we will look into that in terms of PyTorch, right? So let's get started. So before going into the variations, just a basic refresher, like if you have a function which is fx, right? So if we plot this, the function will look like this, and so the function will look like this, and so there are certain positions where the derivatives will be zero, right? So if I take the first order derivative, and these are the points where my derivatives are zero, right? This point, and this point. So all these points, like the 3 points which I have shown here, where the first order derivatives are zero, that can be either local minima or it can be local maxima and also inflection points, right? Or a saddle point. So this inflection points are points where if you go right to this point, there is a minima, and if you go to the another side, there would be a maximum, right? So you cannot decide whether it's a global minima or global maxima, right? So in all these scenarios, your first order derivative would be zero, right? Now how to decide like which are my global minima or maxima, or which are inflection points or the saddle points, right? So then you need to take the second order derivative, and with this criteria, so you can decide whether they are either minima, maxima, or inflection points. So if my second order derivative is kind of greater than zero, then that's a minima, right? And if my second order derivative is less than zero, then that is maxima, and it is zero at the inflection point, right? So you can see like for this point, this is zero, right? And here the second order derivative is positive, right? Which means this is a global minima, right? So if you look into this also, so you can relate these things, right? So this is my minima, this is where the first order derivative is zero, and this is where my second order derivative is positive. Similarly, for this point, the first order derivative is zero, but the second order derivative is also zero. So that means it's a saddle point or an inflection point, right? And for second order derivative for this point, which is a global maxima, so there the first order derivative is zero and the second order derivative is less than zero, right? So this is where the zero value lies, and this is less than zero, right? So this would be my global minima, right? So this is sorry, that would be my global maxima. So the minima is this point where the derivative second order derivative is positive, and this is the point where my second order derivative is negative. So that means it would be a maxima, right? So this criteria, so you should keep in mind, just for your knowledge purpose, you can keep these things in your mind. And now let's look into the types of gradient descent, right? So first one is like stochastic gradient descent, which we also call as SGD. So in this SGD process, the process calculates the error and updates the model for each training example. Like if you are having 100 training examples in your training data set, for each of these training examples, there will be a error calculation. So the error calculation will happen by comparing your actual with the predicted value. Then a step of gradient descent will happen for each of the training examples, right? So as the process goes on for each example in the training set, it has certain downsides, which are like computationally, it's a expensive process, and it also takes longer training time to uh, reach the convergence, right? So after that, what we have is batch gradient descent. So in batch gradient descent, it calculates the error for each training examples, but only updates the model after all the training examples have been evaluated. So it's calculating the errors by comparing the actual with the predicted value for each of the training examples, but it's doing updates after going through all the training examples, right? And the one thing to keep in mind here is this concept of epoch value, right? So in the epoch value, so what this epoch is, one pass through the whole training data set is called epoch, right? So And this epoch value is like with this epoch, you can say that with the definition of this epoch, you can say that in batch gradient descent, after every epoch, we are doing the weight updates. We are calculating the errors for each of the training examples, but weight updates are at the end of the epoch, right? So with this also there are certain downsides because it's accumulating the prediction errors, right? So it requires a larger memory space and the whole data set needs to be in the memory of your computer, right? So the training data set in memory needs to be available to the algorithm at the whole point of optimization process, right? So this is the downside of this too. Like the first one, which is like SGD, has a downside where it is a computationally expensive, and also for batch gradient descent it is also kind of computationally expensive because you need to have the whole data set in your memory for calculating the derivatives, right? And so in between there is a concept what we call as mini batch gradient descent, right? Here we kind of divide our training data set into small batches, and we calculate the errors on that small batch, and then we make the weight updates for those small batches, right? So this in between values where like the small batches are kind of depends on your machine configuration. Based on the capacity of your machine, you can either choose a high value of small sizes batch sizes, or you can choose a low value based on the your system configuration, right? So the upside of this is it is like the model weight update frequency is higher than the batch gradient descent. That's why it allows a more robust convergence, and also computationally it is more efficient while comparing with the SGD or the stochastic gradient descent. It runs much faster than the SGD, right? As I mentioned, like the mini batch sizes, what we call as batch sizes. So that batch size will depend on the configuration of your system, and based on that, you can select the values on a power of two, either 32, 64, 128, or 256, and so on, right? So the batch size is also kind of a slider on the learning process. So the small values of a batch size will take you to convergence more quickly at the cost of a noise in the training process, right? And when you select a very large batch size, then your convergence would be slowly, but it will be more smoother in nature. So if you just look at this two example, this is where the stochastic gradient descent is. So here the learning process is much more noisier, right? And here in the mini batch gradient descent, the it's much more faster convergence, and also the training process is much more smoother. So in nowadays people generally use mini batch gradient descent, and with that they only optimize their neural networks. Right, so there are certain other optimizers are also present, which are like Atom, RMSProp, and Momentum. So this Atom is kind of a combination of your RMSProp and Momentum. And so we will go through in detail like these two algorithms at first, like RMSProp and Momentum. Then using the understanding of RMSProp and Momentum, we will see how the Atom works. So nowadays, like the Atom is kind of a default choice for selecting the optimizer. And this is how we generally define a optimizer in Pytorch. So we kind of using this torch.optim package, we kind of there you can access different optimizers, and based on that you can define your optimizer. So this is an example where I have used Adam. So inside this, while calling this method, you need to pass your model parameters along with the learning rate. Similarly, we can do this also for SGD, right? Now, the question arises why we need a different type of optimizer, right? Whether we have a mini batch gradient descent, then why we need a different type of optimizer, right? So if you try to visualize the optimization process, generally, if we start from this area and our global minima is in this region, so generally without using this type of optimizers like Adam or RMSProp or Momentum, generally the process is much more noisier. So it will kind of oscillate in this way till it reaches the convergence, right? So, but we want our training process to take larger steps in this region and take smaller steps in the this region, right? So with the help of this RMS prop momentum and Adam, we can achieve this process where the training process will be much faster using moving in this direction, and here in this directions we will move slower, right? We will take smaller steps in the upward direction, and in the sidewise we will take larger steps, right? Now let's see how this three optimizers works. So before going into the concept of like Adam or RMS pop or momentum, so it builds on the concept of exponentially weighted moving average. So for an example, like if you write down the equation of exponentially weighted moving average, it looks like this. So the current value, which is Vt, that will depend on the previous value, which is Vt minus 1. That will be multiplied by a parameter, which is B. And then we have our current data point, right? So based on this value, we are calculating the value of Vt, right? And this theta t, which is like the current data point, that will be multiplied with a factor of 1 minus beta, right? Now, if so generally this parameter value, which is like B, that ranges in the loop of like 0 to 1. Now, generally, we select a higher value for this, like say zero point 0.9. So if I just plug in this zero point 0.9, right? So this value would be your previous value will be multiplied with 0 0.9, and your current data point value will be multiplied with 0 0.1, right? So you can see with this concept, you are giving larger or higher weightage to the previous points and lower weightage to the current data points, right? When your beta is quite large. And based on that, your if you try this exponentially weighted moving average and try with different values of beta, it will look like this. For beta equals to 0 0.9, your the plot will be much more smoother. And with lesser value of beta, which is like 0 0.6, your the plot of this exponentially moving average would be much more noisier in nature. So if I try to relate with our gradient descent algorithm, so if we just plot the contours in this way, so we want our directions to be much smoother in this region and much smaller in this directions, right? So with the help of this concept, we will try to increase the momentum in this direction and will decrease the momentum in this upward direction of while doing the convergence, right? So with this concept of exponentially moving weighted average, let's see how the momentum works, right? So generally in case of gradient descent, we do the weight updates using this two formula, which we talked a lot in previous sessions. Like previous W, we subtract the value of previous W value. Then we multiply the learning rate with DW. And similarly, we also do it for the beta or the bias term, right? So now in case of momentum, what we do is we kind of remove these two things and we replace with VDWT and VDBT, right? So these are like T denotes the current value of my parameter value, right? Or the derivative of my current parameter value. Now, what are these VWT and VDBT? Let's see. So this is how we generally calculate based on the same formula which I discussed in the last slide. So here we introduce a parameter which is beta, and based on that we give a higher weightage to the previous value of my VDWT minus 1 and a lesser weight with the current derivative which we calculated, right? With the hope of that we will move faster in the horizontal direction, and we will move slowly in the vertical direction, right, while doing the optimization. So as I mentioned, the learning would be much more smoother with this concept, and we will hope that the learning will be smoother in this vertical direction, and the horizontal directions we will move slowly, right? Now with that, let's come to the another concept, which is RMS prop. So in this RMS prop, the same concept remains. Here also, we will kind of replace this DW and DB with a new set of equations. Here we are using the current derivative, which is DW, but we are dividing with a value of root square of SDW. And also we are, for bias term, we are dividing the DB with a value of square root of SDB, right? Now let's see what this SDW and SDB is, right? So with the same concept of exponentially weighted moving average, here we are just squaring my current value, current DW, right? So you can see like the current DW we have squared, and also for bias term also the derivative we have squared. And then we are plugging these values inside this RMSProp equation, and we are doing the weight updates. So here also the idea is to move very fast in this direction and restrict the movement in the other direction, right? So with the concept of this too, here in the RMS prop, just that we are squaring our derivatives of weights, derivative of loss with respect to the weights, and we are just having a square of those values in the equation, and the value which we are getting like SDW and SDB that we are using to divide the current derivative. Right. So with this concept, now let's see how the atom works. Now, in modern day, like atom is kind of a default choice of your optimizer. Now, this is what momentum is, and also this is what the RMS prop is, which we discussed in the last two slides. Now, in case of atom, what we do is we use both these two things, my VDW and also the SDW, the square root of SDW. So we use the VDW here, and also we use the SDW, right? And we incorporate these two things, and the hope is that with the combination of my momentum and RMS prop, our learning would be much more smoother and much more faster while comparing with the other optimizers which are available, right? Now this VDW is coming from the momentum, and this SDW is coming from the RMS prop, right? And we also introduced two different beta terms because we have betas coming from my momentum and RMS prop. So the beta associated with momentum, we are calling it as B1, and beta which is associated with RMS prop, we are calling it as B2. Right. And generally we set these values as the default value works well, and the default values are in the range of like beta 1 equals to 0.9, and beta 2 is around 0.999, right? So with this, we hope that you got an understanding of the different optimizers that are available. Like we started, let's just to give you an like a recap of what we discussed. Like we started with stochastic gradient descent. And then we talked about what are the downsides of stochastic gradient descent, then which is like it's doing the weight updates for each training example. Then we discussed batch gradient descent, where it's only updating the weights after completing the epoch. It also has certain downsizes that it needs to accumulate the prediction errors at the memory, and whole training data set needs to be at the memory at the whole optimization process, right? So in between, we kind of went through an approach which we call as mini batch gradient descent, where we kind of divide our full training data set into small batches. And on top of those small batches, we calculate the gradients and do the weight updates, right? Then we talked about the few other optimizers like ADAM and RMS prop. With the help of exponentially moving a weighted average, we try to understand the concept of this three things. And in the end, we talked about what is ADAM, right? So ADAM is kind of a combination of momentum and RMS prop, and we kind of incorporate both the concepts in the ADAM, and we hope that our learning would be much more smoother. So yeah, thank you all. Thanks for your time. See you all in the next video.